So basically, they've come up with this group relative policy optimization. This is like a reinforcement learning framework. And as you can see, in this framework, you have basically an objective function that you're trying to minimize in some meaningful way. Uh, so, so just to understand this objective function, this equation one of the R1 paper, and let's say the equation three of the R1 paper, can we go to that? This is the objective function. This is what is called the objective function plus the Lagrangian, right? Beta is the Lagrangian, and the constraint is the KL divergence of pi beta to pi reference. Pi reference is pi sub theta old to. So what it's trying to say, there are two probabilities here, and it wants the constraint to be uh, the distance between the two distributions. And the way you measure the distance between two distributions, you do what is called KL divergence, as opposed to Euclidean distance or Wasserstein. You can also do Wasserstein distance. You can do what is called an optimal transport, but they do KL divergence because KL divergence doesn't have any units as opposed to Euclidean distance. So it's basically a notional uh, value of the difference between the original probability value or distribution value to, let's say, the empirical distribution value that you would compute. That is the constraint. And whatever is the constraint, you add that to the objective function with a Lagrangian beta here. Okay, this is how, if you don't know anything about optimization, there is always a function that you want to minimize or maximize. And then you minimize or maximize that function with respect to some constraint. And then what you do, you use both of them, the objective function minimization is a dual of, let's say, working with the penalties when you assign the Lagrangian with respect to some constraint. So you add the constraint on, and that solving that constraint laden objective function is equivalent to just barely minimizing the objective function without the constraint. That's the broader idea of all optimization techniques. So if you go to what I've written down, yeah. So what I think this first function on the left-hand side that you can see is, can you move the cursor so that like I can't? Yeah. So this basically is like the objective function, which is, again, to understand this, you go to the second page of the previous one. Yeah, the policy gradient is basically, so here you're getting a gradient function wherein it's gradient of log of the probability of an action with the advantage given the state, action given the state multiplied by the advantage function. Okay. So advantage is, so in reinforcement learning, the whole idea is you come up with a policy function, and the policy is the real life experience of an actual agent, and the agent's the agent's, let's say, essence is to optimize the policy function to its benefit. As soon as the advantage becomes negative, it will stop doing that action. It will go back to other actions in the class of actions where its advantage function is positive. Okay. So the loss function that he takes into account is the loss function that I've written here. The expected value of log of, let's say, this probability value multiplied this probability value of action AT given state ST multiplied with advantage AT. Okay. The cap has got to do with the fact that these are all empirical values. Is every time there is a cap in any of the formulas, it basically means that you're taking a bunch of samples. In this particular case, let's say samples with respect to T, and you're taking those samples and you're actually computing the average. Okay, and when you differentiate this, basically it's whenever you have log x, it's one by x is the differentiated form. And then the chain rule essentially tells you that you one by the probability function, and then you multiply that with the differentiation of the actual thing which comes on top. So when you differentiate the loss function, you get a gradient function which is equivalent to the gradient which is equivalent to the policy gradient that we had at the beginning. Okay, and if we go to the next page, so essentially what he's trying to say is, so here he is trying to say that if you even if you have log of probability function which is computed, this is equivalent to ratio of probabilities, wherein pi sub theta is the new action that you take as a result of your first step, and pi theta old, it's actually theta that is missing here, pi sub theta old theta, which is the previous, let's say, policy function, and the policy function changes after every step. Okay, and the action functions are essentially action, or let's say state actions are 80. So every time you go from one state to another, you compute the policy function all over again and make sure that it is your overall direction is positive, meaning like you're optimizing your let's say you're optimizing whatever you're optimizing for. Let's say you're optimizing for food or you're optimizing for money. You do the action and you count how much money you had previously and how much money you have now, something on those lines. So here, basically, I've written what happens if you take a gradient of a log ft. This is again example explanation of what I did in the last step, wherein if you take a gradient is differentiating a function, and if you differentiate a function, it's 1 by f of theta, and then you differentiate the individual function on top. So here, what it's also saying on the right hand side of this is that you sample from the old. This is the thing that I usually tell you in any class or any place I meet anybody. I have to explain something about probability. Probability has got to do with conducting random experiments. In those random experiments, there is, let's say, coin toss. You do 2 coin tosses, and your job as part of the sampling exercise is to generate the samples without actually having the coin. So assume that theta old is one of the coins which generates some sequences, and your job is to come up with an action sequence, which is another sample, which is not from the same sample, but from a different distribution. And your job is to be as close as possible from the first distribution. You don't want to go too far. Another thing that I wanted to explain here, if you go to the next, I haven't have I written anything in the next. Oh yeah. So this is where so the objective function is what you see here. You want to maximize the expected value of this ratio of probabilities, pi theta and pi old theta. So pi theta old is the old policy function. Pi theta is the new policy function after taking a step, right? So every time you go from 1 to 2, you take the policy function ratio of 1 with the numerator 2 by 1. So you take another step, you compute the policy function again. And then, as I pointed out, the term written in red is the objective function, and the term written in the black ink is the constraint. So if you go back to the actual R1 paper, can you go back to the R1 paper? Keep this and go back to. So if you look at what these people have done, this is essentially the same thing I've written there. So it's a ratio. You're minimizing an objective function as a ratio of probabilities, and you're constraining it with a KL divergence, which essentially says that you're not going too far away from your original probability. And the reason they do it, can you go back to what I've written? Yeah, so can you go back to the next slide? We'll come back again. Have I written anything in the next slide?
This is the final one.
Oh, there was one more slide. I didn't write anything there. So can you go Google trust region policy optimization? Or you can just type it on Google. I mean, we won't get into all the technicals, but basically what it's doing, yeah, this is the main paper on which this whole reinforcement learning work is built on. And I think he's in OpenAI, or he was in Berkeley, but John Schulman, he's quoted a lot in the R1 paper. He graduated from Berkeley and he started working in OpenAI. So when people say, "Oh, this R1 paper has completely upended OpenAI's work," he's the inventor of the main method that is getting used in R1 paper, and even R1 paper people refer to that. So his main technique is what we call trust region policy optimization, right? TRPO. I think it's in the second half. Do you see TRPO? Yeah. So he's got an entire derivation and entire paper on this. And also Michael Jordan is listed in this. So he's like the godfather of, let's say, all of machine learning for the last 30 years. I think he must have done his PhD under him. Yeah, are you guys familiar with Jordan at all? But
No.
he's the Michael Jordan of machine learning, so to speak, like the way Michael Jordan.
Okay, that's a good way.
Okay, so can we go back to the or in this paper, can we scroll down? Do we have? I wanted a diagram, if it is available.
This one?
No, I don't think it's there here. Here, okay, in this preliminaries, right after the paper, they write some derivations, right?
This one?
Yeah. So before this, yeah. So I think somewhere he explains. Probably we can explain it some other time. So this Sham Kakaday's paper, which is 2002, which is also a good paper. All this is basically you can look at numerical optimization, and there's a very popular reference numerical optimization. What's the famous book? Wait, let me tell you the.
This one?
Probably we can put the name of the book in the references. But the point here I'm trying to make is if you can, in usual gradient descent algorithm, you have a policy function, and if you optimize in the direction of the gradient, you optimize as much as possible. In this particular algorithm, you cannot do that. If you do that, you go far away from the actual objective function. So what they do is they ensure that you only go in the direction within the trust region. So that's why there is a constraint. So you want to optimize in the direction of the gradient, but you don't want to go all the way and exhaust everything that you need to optimize. That's why the constraint here is you need to go in the direction of the gradient, but you don't go far away in the trust region. That's why there's a constraint in terms of how far you can go, and that constraint is captured by the KL divergence. And the usual technique of in optimization is you have an objective function and you have a constraint, and you use this the what it's basically saying is the last line that I've written, right? The optimality point of let's say the constraint problem is also an optimality problem point of beta. So meaning solving what's in red is equivalent to solving the combined problem. Okay, so this is how they use let's say this is a way by which they can solve this problem by using what is called a penalty problem, meaning like you can so what it means is if you go too far away, you can penalize that function to a point wherein it comes back within the trust region. That's what this essentially means. So broader idea of, let's say, people who are not familiar with optimization, solving what's in red is equivalent to solving the combined red and black, which is there in the third equation. So if you compare the third equation with 3 in the R1 paper, it's pretty much the same. Okay. And they have come up with an interesting method to solve it, as has John Schulman's paper in 2017, 2018. Okay, that's the technical stuff of R1.
So that's all the content we have for today.
Okay, so can we go back to the last slide of so, and these are like some of the benchmarks that they have. You can probably play this and we can wind up with that.
Yeah, this is the same video that we played, so it's fine.
Oh, it's the same video. So, and these are like the benchmarks that the DeepSeek has done with OpenAI.
Yeah.
Okay. Can we go to,
the
is this
only
the last
thing,
slide?
yeah, this is the last slide. I think the only thing where R1 kind of is worse than OpenAI is the GPQA diamond. I think in the first few podcasts we discussed what GPQA diamond was.
You
So,
want to recapture that for like in a line or two?
yeah, so GPQA diamond. So these are all, so whatever those names that you saw in these tables are, they're all benchmarks. So these are benchmarks, not necessarily just for LLMs, but MMLU is for LLMs, and all of these others are for like human and LLM. But GPQA Diamond, it's like really hard math questions and all of that.
Oh, that's great. So I think we can probably take a look at it some more time. So
Yeah.
I think that's pretty much it for this week. This week was the entire news was about DeepSeek and its impact to our natural world, and hopefully we will have more updations in terms of the updations that are there in the world of AI, and anything that you as viewers, if you encounter something, please leave in the comment section what you think we should cover. We'll probably do it in the next session. Thanks, Dan, for joining. See you next week.